Alright, so we're starting a new chapter here. It's going to involve sequences and series and adding things up. So just a little bit of review here to start off. This whole front page is not calculus per se, but it's just reviewing some things we're going to need. So the little subscript tells us what number in the list we are. So if we just had the counting numbers 1, 2, 3, 4, 5, then a sub 1 would be 1 and a sub 2 would be 2. So this just says list the first 5 terms, so all you have to do is put a 1 in, and that would be 3 plus negative 1 to the first power, so that would be 3 plus negative 1, so that would be 2. Then we're going to plug in a 2, so if we square that, that's going to be positive 1, so 3 plus 1 is 4, and go back and plug in a 3. That's just going to be 2. It said the first 5, so 4, we'll make that 4, and finally a sub 5, that'll be negative 1, so that'll be 2. So that's pretty much it for that, so that's pretty basic. Over here, a sub 1, so we plug a 1 in there, that's going to be 1/2, and a sub 2, that'll be 1 over 2 squared, which is 1/4, and then 1 over 2 cubed, which would be 1/8, and then 1 over 2 to the 4th, which would be 1/16, and then 1 over 2 to the 5th, which would be 1/32. And that's it. So they just asked us to list those numbers. Now, a recursive definition is where you're given the initial term and then each term is defined by the term before it. So what this is telling us is that our first term is negative 11, and then what this is telling us is that any term is equal to the term before it plus 5. So to find the second term, so if we wanted to find a sub 2, if you look at this, that would be a sub 2 minus 1 plus 5, or a sub 2 equals a sub 1 plus 5. So it just says, basically add 5 each time. So if we add 5 to that, that would be negative 6, and add 5 to that, and add 5 to that, and add 5 to that, and we're done. And basically, this one is multiplying to get a number. You take the number before it and multiply by 2. So that would be 6, 12, 24, 48. And this last one is, now it looks a little tricky, but they rearranged some stuff here. So the first number is 25. Now, this is still, d sub n is the number that occurs before d sub n plus 1. So we're just subtracting 5 from the number that occurred before it each time. It's the same relationship. N is 1 past n minus 1, n plus 1 is 1 past n. If you think about it, it goes n minus 1, n plus 1, n plus 2, n minus 2, etc. Alright, so let's look down here, and we see this, and we all have had several math classes, so we all know that that is n! Did I get you? Alright, just kidding. That's n factorial. That was a little English joke there. All right. So you don't have to shout when you say it. The exclamation point in math means factorial. It means that you're going to multiply all the factors out up until that number. 0 factorial is defined as 1. It doesn't really come up much, but if it ever does, it's 1. And if we want to write n plus 1 factorial, that's kind of what I was actually just writing up here, we would go to that. 4 factorial is 4 times 1 times, is 1 times 2 times 3 times 4, or you could say 4 times 3 times 2 times 1, but That's fine. Okay, so let's work on some of these. So what I like to do in this situation is I like to realize that, okay, so 3 factorial can cancel out, and then I'm going to have 8 times 7 times 6 times 5 factorial. Okay, I see a 5 factorial down there, so that's going to cancel out that 5 factorial. 4 factorial, that's going to be 4 times 3 factorial, and then 5 factorial. Okay, so I left, so the 3 factorials are going to cancel, and the 5 factorials are going to cancel. That leaves us with 8 times 7 times 6 over 4. So 4 over 8 is going to reduce to 2 over 1. So that's going to be 42 times 2. So that's going to be 84. So that's what we want to do there. All right. Okay. So if we move on to the next one here, that's really not that big of a deal at all. The n factorials cancel, and that's just 2. Now, this is a little bit trickier, but hopefully not that bad. So we have 2n plus 2 factorial. So what we're trying to do is kind of accomplish the same thing that we did over here. So if we step this back a couple levels to 2n plus 2 factorial, and then the next number would be 2n plus 3, and the next number would be 2n plus 4, which would get us up to there. That's going to cancel, so that's going to be 1 over 2n plus 3 times 2n plus 4. And we don't need to multiply that out or anything like that. So on these, we're just going to be kind of doing something similar to what we did there. We want to try to cancel something out. So if you think about this, this would be 2n factorial, and then the next number after that would be 2n plus 1. So if that was, same thing, if that was 10 factorial and we wanted 9 factorial times 10, 2n plus 1 is the next number after 2n. So those are going to cancel, so it's just going to be 2n plus 1. Okay? Now here, if you think about it, 2n minus 1 is the number before 2n. So we have 2n minus 1. Now, the number before 2n is 2n minus 1, the number that occurred right before that. And then the next number is 2n. So just like we separated this 8 factorial into 8 times 7 times 6 times 5 factorial by going to the numbers before it, same thing here. The number before 2n is 2n minus 1. So those cancel. That's just going to be 1 over 2n. Alright, so we're going to be spending a lot of time on deciding whether things converge or diverge in this chapter. So basically, if the terms approach a certain value, then they're going to be said to converge. For example, this approaches 0 as n approaches infinity. If they don't converge, if they don't approach a specific number, then they're said to diverge. Okay? So, it says evaluate the limit of that. So, all we're doing is what it told us to do. So, we're taking the limit as n approaches infinity of -1 to the n minus 1 power. Now, if you plug a 1 in there, you get 0 and you get 1. And then if you plug 2 in there, you get -1. And then if you look at that, so you can see that keeps bouncing back and forth, so it's not approaching one thing. And since it's not approaching one thing, we're going to say that that diverges. And we're done. Alright? So, if we look at this and we take the limit as n approaches infinity, it's going to be 2n squared over 5n squared minus 3. Now, using pre-calculus, we can figure that out like right now. Using top heavy, bottom heavy, or equal. They're equal, so this is going to approach 2/5. Now, that's not really showing much calculus, so if we want to show some calculus there, one thing we could do is divide those all by n squared. So that would be 2 over 5 minus 3 over n squared. And we could do that instead. And so as that approaches, that's going to be 2 and 5 minus 0. And so I'm going to say or, but really we want to do one of these because that's not really showing the calculus there. So, or we could realize that this is going to be infinity over infinity. So we can use L'Hopital's rule. So if we do that, that would be 4n over 10n. And that would still be infinity over infinity. So we could do the limit as n approaches infinity. That was also infinity over infinity. So take the derivative again, you'd have 4 over 10, and that equals 2/5. So that's infinity over infinity, so we did this. That's infinity over infinity, so we did that. Okay? So we take the limit as n approaches infinity of this. We get infinity over infinity. So it's so important, we talked about this last year, when they take points off if you don't show the limit of the derivatives. So when you use L'Hopital's rule, you want to make sure that you do that. Now you might not remember the derivative of a different base, but it's just the natural log of that base times the and that works for e as well, because e to the x, we would be multiplying by the natural log of e, which is 1. So, but if you plug in infinity here, you still get infinity over infinity. So if you take the derivative of the numerator and the denominator again, you're going to get 2 over, and now we're going to have the natural log of 2 squared times 2 to the n. So if we let n approach infinity there, that's going to be 2 over infinity, which is 0, which means that sequence converges. So this gets smaller and smaller and smaller until it's pretty close to 0. Okay? Alright, so limit as n approaches infinity of ln of n over n. It's a little bit awkward, but that's going to be infinity over infinity. So L'Hopital's rule again, so n approaches infinity. The derivative of that is going to be 1 over n, and the derivative of that's going to be 1. So that's going to be 1 over infinity. So just writing it out in a little more detail, the sequence converges to 0. That's the same thing we could have said there. The sequence converges to 0. We said the sequence diverges. Here we could have said the sequence converges to 2/5. There. All right. So here, if we want to take the limit as n approaches infinity, but what we can do there is change that to n factorial over n plus, or times n plus 1 over n factorial, adjusting those factorials. So those cancel. That's going to be infinity plus 1, which is infinity. So we're going to say that that sequence diverges. And here, I'm going I have the limit as n approaches infinity, and the numerator n plus 1 factorial, denominator n plus 1 factorial times the next number, which would be n plus 2, times the next number, which would be n plus 3. So those cancel. It's going to leave us a 1 up there. So as that approaches infinity, we're going to get infinity plus 2 times infinity plus 3, which is infinity. So that sequence converges to 0 also. And then we just have some properties of limits that are also true for sequences. All right, so the squeeze theorem for sequences. We had a squeeze theorem for limits before, a long time ago. But it says if we have a limit of one sequence, so I'll say that could be the red points there, and the limit of the blue points, if they both have the same limit, and at some point along the way, starting at some point, all of the points of this new limit are in between the points of the other two, then that limit must be the same. So I tried to show it here with purple, but it didn't show up, so I highlighted them. You can see them, maybe you can see them highlighted in yellow. So at first, so we have the red one. Oh, I did those backwards. The red one and the blue one. Here it says the red one's less, so I guess I switched those up. So the blue one is the one that's less, and the red one is the one that's more. Okay, so what we're saying here, so you notice that the yellow, the C, is more than the red here, and then it's in between here, but then it's below the blue here. But then at this point N, where I drew the purple line, after that point, now it's always in between the other two. So as long as some point it starts to stay in between them, then we can use this squeeze theorem for sequences. Okay? So that's the main idea. So if we look at this, this should be oscillating back and forth. So if we think about it, if we take -1 over this, then this should always be in between these two things, which is just the positive and negative version of that. We're going to be jumping back and forth, but it's going to be equal to or greater than that one and equal to or less than that one. Okay? So if we take, I used blue for the last one, so if we take the limit as n approaches infinity of -1 over n factorial, well, that's going to be -1 over infinity, so that's going to be 0. And if we look at the other one over here, take the limit of that as n approaches infinity, that's going to be 1 over infinity, so that's also going to be 0. Okay? So by the squeeze theorem for sequences, C of n converges to 0. All right. Find the nth term of a sequence. So a sub n. Now I can see that this is alternating. So I can put a -1 in there to the n power because the first term is negative, so if I put a 1 in there. So I've got that covered. Now, if you look at the denominator there, you might notice a pattern there. 1, 2, 6, 24. So multiplying by 2, multiplying by 3, multiplying by 4, multiplying by 5, that's factorial. So that's just going to be n factorial. Now the numerator is a little bit trickier, but these 5 numbers are all close to a pattern of other numbers. 81, 26, 8, 2, 242 you might not notice, but I'll give you a hint. It's one number away. If we were added 1, we would be onto a pattern. So if we add 1, that'd be 3, 9, 27, 81, 243. So hopefully if you're thinking about that here, this is going to be, that is almost 3 squared minus 1. This is 3 to the first minus 1. This is 3 cubed minus 1. This is 3 to the fourth minus 1. So you can compare that to 3, 9, 27, 81, 243. So that is 3n minus 1. So that's the first part of it. It says find, so that's the sequence. And then determine a value of a sub 6 and determine whether it converges or diverges. So a sub 6 is going to be negative 1 to the 6th times 3 to the 6th minus 1 over 6 factorial. So that's positive, so that's good. This is 720, 120 times 6, 120 times 6, and 3 to the 6th, so 729 minus 1 is 728. We could simplify that if we wanted to. I don't really want to. Now, does that converge or diverge? Well, let's think about it for a moment here. So basically, we're multiplying, let's focus on 3 to the n, because 3 to the n minus 1, the minus 1 is pretty insignificant. So 3 to the n would be 3 times 3 times 3 times 3, etc., right? And n factorial would be 1 times 2 times 3 times 4, etc. So if you think about it, that's 9 over 2, but after that, we just keep multiplying by 3, but down here we multiply by 5, and then 6, and then 7. We keep increasing what we're multiplying by on the bottom, whereas this is going to stay constant. So this is going to overtake that much more rapidly. N factorial grows faster than 3 to the n. Okay? That means that the denominator is going to get much larger than the numerator. So if the denominator is much larger than the numerator, this is going to get really big. They both get large, but this gets much larger. So, the sequence converges to 0. Okay? Denominator is going to get much larger than the numerator. So if a sequence is strictly increasing or strictly decreasing, we call it monotonic. We brought that up in AB. If there's a number that all of our numbers are above, then it's said, we say it's bounded below. It has a lower boundary if all of our numbers are above that. If it's bounded above, if there's a maximum that all of our numbers are below that number, that's an upper bound. If it's bounded below and above, then we just say it's bounded. Okay. So to figure that out, we want to compare to the next number. So we have n, and we want to compare that to n plus 1. That will give us some information about the situation. Okay, so determine if the following sequences are monotonic and or bounded. So first thing we could do is we could plug in a couple numbers. So if we plug in 0, we get 0. If we plug in 1, we get -1. If we plug in 2, we get -4. Probably enough to see a little bit of a pattern there. So now we want to compare. So we want to take -n squared. We want to compare it to -n plus 1 squared. We want to say which one's larger. So if you think about it, these are both negative numbers. The absolute value of this is going to be larger than that. So you could take a practice, you could try it. So 4. So that would be -16. This is going to be 4 plus 1 is 5. That's going to be -25. So 25 sounds larger than 16, but it's negative. So -25 is on the number line down here. Number 16 is closer, -16 is closer to 0. So actually, the -n squared is larger. Okay? So that means everything is going to be below it. So we can see there, it's decreasing. It should always be decreasing, so we could say it's monotonic. It's our last page. We're almost done here. Yeah. All right. Bounded above, if it's always decreasing, that's the biggest number, so it's bounded above by m equals 0. And it just keeps going. So it diverges. All right, so let's try it again. So if we plug 1 in there, we get a +1. If we plug 2 in there, we get a -1, +1, -1. So that's not increasing or decreasing. So it is bounded. So we just say it's bounded because m equals 1 above and m equals -1 below. So we just say that it's bounded, and it's not approaching a specific number, so it diverges, kind of bouncing between those. Okay, so if we plug 5 in here, we're going to get 2/25. If we plug 6 in there, we're going to get 2/36. Now, you may be thinking, well, why don't we reduce that? Patterns are one of the few times where it might not be a good idea to reduce, because when you reduce certain terms, then it might not be as easy to see the pattern that exists between the numbers. So pattern questions are kind of one of the few exceptions where we don't necessarily want to reduce that. I don't think they said how many we have to do, so I'm looking at the directions. No, so that's it. So now we want to compare that to the next one. And we want to think about what happens there. Now, hopefully you realize if we have the same numerator, but the denominator increases, that's going to make that smaller than that. It's like smaller pieces of pizza. Okay? So, out of how many? That's a fraction. It's out of how, 2 out of how many? If we're going to cut the pizza into more pieces, then the pieces are going to be smaller. Okay. So, that is decreasing. It is monotonic. It always decreases. And it is bounded above. So first of all, it's bounded. We'll talk specifically about that in a minute. It also converges to 0. So if you think about that, the numerator is not changing. The denominator is going to keep going up and up and up and up. And so we divide that, that's going to be 0. Now, let's talk about bounded some more. So it's bounded. So the biggest it can be is 2 over 25. So it's bounded above for m equals 2 over 25. But it's bounded below for m equals 0. Because there's no number you can plug in there that's going to make that less than 0. Actually, we're not even going to get to 0. So, okay. 2 more. All right. So, how do we want to look at this? Plug a 1 in there, that's going to be 1/2. We plug a 2 in there, that's going to be 2/3. We plug a 3 in there, that's going to be 3/4. Okay. So, looks like that is increasing. Now it looks like it's increasing, but what if we took the derivative of it just to make sure? So low d high minus high d low over low squared. So that's going to be n minus n. That's going to be 1 over n plus 1 squared. Okay. Well, that is the derivative. And so that is always greater than 0. So I probably should have given that a name and said that was y equals or whatever before I did that. So the derivative is less than 0, or greater than 0. So its function is increasing. Okay, so we are increasing and monotonic. And if we think about this, bounded, it is bounded. The most it could ever be, the numerator is always less than the denominator. So it's never going to reach 1. It's always going to be less than 1. So it's bounded, and we could say it's bounded below okay. I think I want to do this here. So it's bounded below by m equals 1/2 and above by m equals 1. It's never going to get to 1. Now if we want to be a little more specific, I was about to do a converge, whether it converges or diverges. We could go back to the way we were doing that before, and we could take the limit as n approaches infinity. Okay, so that's going to be infinity, actually negative infinity, so that's why that diverges. Okay, and here, if we take the limit as n approaches infinity of this, that doesn't really help us goes back and forth, so that diverges also. Here, we take the limit as n approaches infinity of 2 over n squared. We're going to get 2 over infinity, which is 0. Okay. And now on this one we can do the same thing. So we can take the limit as n approaches infinity, and that's going to be n over n plus 1. So we could say that that's infinity over infinity. And so since it's infinity over infinity, we can take the derivative. And that would be 1 over 1. So that's 1. So this converges to 1. Okay. Last one. Let's see. So n cubed is always going to be less than n to the 4th plus 10,000. So it's bounded above by m equals 1. It has to be less than 1. Alright. Now, let's see. Let's look at some numbers here. So a sub 1 is going to be 4 zeros and 2 nines. 1, 2, 3, 4. A sub 2 is going to be 3 zeros and a 7, 9, something. A sub 3 is going to be 2 zeros and a 5. These are ones I prepared earlier. So I guess I should put approximately there. Dot, dot, dot. Okay, so if we go down to a sub 10, that's going to be 0.05. Okay, so if we look at that, it looks like it's increasing. So this is kind of above and beyond even what we're going to have to do, but we're going to take a look at it anyway. So what we're focused on here is this can be deceptive. So let's take a look at this as a function. So if we had f of x, that's what I could have done over here too, change those to x's, but it's okay. So our function is x cubed over x to the 4th plus 10,000. Alright, and if we take the derivative of that, low d high minus high d low over low squared, then we can factor out a negative x squared. So that's going to look like this. And that's going to be over x to the 4th plus 10,000 squared. So if we look at the critical numbers of that, that's going to be x equals 0 and the 4th root of 30,000, which is approximately 13.1607. Okay, So what we'll see there is that at 13 it changes, the derivative changes signs at that critical number. So what that means is that we're increasing from 0 to 13. But then after that, we're going to be decreasing for n larger than 13. Okay? And then, so that's kind of odd. We have those two different situations. That's unusual. It's not going to show up. It shouldn't show up. But and so then the last thing to look at is the limit as n approaches infinity of that. So that's going to be n cubed over n to the 4th plus 10,000. So if we divide all of those by n cubed, we would have 1 over n plus 10,000 over n cubed. So when that goes to infinity, we would have 1 over infinity. So it converges to 0. Alright, so if that lost you a little bit, that last one in particular, don't worry about that too much. That's a challenge question. So, alright, it's about that time.